Hello world, it's Craig. I'm still halfway through testing this new 8085 based single board computer for the STD bus, and I was porting my confidence test over to this machine, and I thought I would stop and do a video on writing a simple breakpoint utility. It's not that big of an effort to write a breakpoint utility from scratch. It can be extremely educational, and a breakpoint utility may be one of the most powerful tools in your diagnostic toolbox, even rivaling your logic analyzer if you use one. Fundamentally, the breakpoint allows the program to run unimpeded until it matches a specified set of conditions. Once these conditions exist, the breakpoint stops the program and returns control to the user. Typically, when the control is returned to the user, there's also a mechanism to allow the user to see and modify the values of internal registers, the stack and stack pointer, the program counter, the flags, and the like. So even if you've never utilized a breakpoint utility, I think you can probably imagine the power it gives the user to interrupt a program, tweak the current status, and then put the program back into motion from where it took off. Now, most good resident monitors or diagnostic tools will offer at least a simple breakpoint control. However, when developing code, especially on a bare metal system like for this STD system, you may not want to be working under the control of a monitor. Generally, I think it's worth the effort to include at least a minimal breakpoint tool into whatever code you're developing. And once you create a good breakpoint tool, those routines can easily be added to your main program during the development stage and then taken out later. Now we can summarize the concepts of a breakpoint controller with just a sentence or two. We have a little program that's running, and the user determines the instruction that they want that program to stop. The Breakpoint Manager is then going to replace that instruction with a restart opcode. And now as the program is running along and it gets to that target address, instead of getting the user's instruction, the processor fetches the restart instruction, and as a result the program is redirected to the address that's associated with that reset or that restart. And the Breakpoint Manager can get as elaborate as you want with extra features like displaying and modifying the system values seem obvious, but you can make it as complicated as you would like. So after the breakpoint is caught and any registers are modified, then when the user is ready, they can have the Breakpoint Manager proceed, and the manager will go back to where that restart opcode was put in, and it'll take that back out and put the original opcode in its place. So now the program can just start at that opcode and continue executing as if nothing happened. Now when you're developing code, you can do this manually, of course, by just putting in a restart and manually taking care of this. But it's a good exercise, and there's nothing like writing yourself a nice breakpoint manager that you can then port over to all of your projects and modify it to your liking and keep for a long time. So let's write the simplest of all breakpoint managers. If there's interest, we can come back and add features to this manager, but it'll be good to see the skeleton manager and how that works. Now as a part of testing this STD board, as I said, I already ported my standard confident test over to this, and then I went back and I cut out or I commented out my breakpoint code so that we could start from scratch and just have a simplified breakpoint manager for this video, because that's going to be much easier to understand than a complicated one. Now my confidence test already has a command handler, and this is what the user sees when they're in that confidence test. And in this command handler, I have a go command to start the program running at a user specified point. So we already have the capability to run the program after we've set the breakpoint. All we need to do is put in the breakpoint manager that configures that breakpoint and the handler that handles that breakpoint once it's hit. To manage the breakpoint, we need to reserve 3 bytes in RAM. 2 bytes for the target address and 1 byte to save the original opcode value. So before we get to the manager, let's slip in a reservation in RAM. Let me go up to where my RAM reservations are. Here we are. And I have this one entry, made a breakpoint table, little data string. I reserved 3 bytes for this breakpoint table. Okay, so that 3 bytes will be enough to hold 1 breakpoint. Now to the breakpoint manager, which in this simple version only needs to do one thing, and that's to allow the user to set a breakpoint. What we're going to do is we're going to ask the user for the target address. This call will send the text starting at the address loaded into the HL to the user. The user then enters a hex address. This call gets and tests the user's response to make sure that they put in a valid hex address. But if the user wants, they can enter a carriage return if they just want to abort. So when that routine comes back, we have to test for the 0 flag to confirm that we actually got a valid address from the user. And when that comes back, in addition to that flag, the address that was provided by the user is going to be returned in the HL pair. Now the shld command saves the address provided by the user as the first 2 bytes in our little RAM area that we reserved, so our breakpoint table. And since the HL is also our memory pointer, it's already pointing to the opcode that the user wants to break. So all we have to do is to get that opcode using the move from memory, and then save that opcode into the 3rd byte of our little RAM area that we reserved for the breakpoint table. So those are our 3 bytes. We have the address and the original opcode. Finally, the last thing we need to do, and that's the whole objective, and that is that we replace that original opcode with the restart opcode. And we can use any restart, but I'm using restart 2. So we just do a move immediate and put the opcode for restart 2 into that memory location. And that's it, we're done. We jump back to our command handler. So that's all there is for the Breakpoint Manager. The user can now pick an address to set the breakpoint, and the next time their code hits that address, it will trigger that restart 2 that'll trigger the breakpoint. But there's still 2 things we have to do. First, we need to redirect that restart, and then we need to actually handle that restart when it comes. So let's look at the restart first. Restarts are 8 bytes apart starting at 0, so restart 2 will be 2 times 8 or 16 bytes up at address 10. So where we have our restarts, so here's our org at restart 2, which evaluates out to 10. If we want to also use the next restart for something, we can fit in 8 bytes of code here. A simple jump just takes 3. We can do a little more overhead here before we jump up to our breakpoint handler. But if we aren't using the next restart, we can fit 16 bytes of code and so forth. In practice, if we're not using any of the other restarts, we can often fit, or we can fit all of the code for the breakpoint handler down here, since the restart 0 in this code just jumps over and continues to some point further up in the main program. But I didn't want to modify my code too much, so let's just put the jump in here that takes us up to the breakpoint hit code that we've stashed someplace up in the EEPROM. And you know, the fact of the matter is nowadays it doesn't haunt me to just leave these extra bytes down here in the restart vector table empty and just waste those unused bytes, since it keeps my code together in one spot and it makes it easier to work with. You know, generally the days of fighting for every byte are over, so I'll just leave these empty bytes down here and live with it. All right, so we filled the restart vector table. When our restart 2 is hit, the processor pushes the address of the next instruction onto the stack, and then it jumps to the address 10, where it will hit this, which tells it to then jump up to the program where we have our breakpoint hit handler, and that is up at 01C6. So let's go up to 01C6 to our breakpoint handler. Now let's look down at our breakpoint hit code. All right, 01C6. This is where the code's going to go after we hit that reset, and that reset kicked it on up here to 01C6 with a jump. Now when we get up here, we get hit with a little minor challenge, and that is that when the restart was serviced, as I said, it pushed the program counter onto the stack, and the program counter had already been incremented. We don't know what that next byte is. It might be an instruction, or it could be part of the operand, but at any rate, the program counter has already been incremented up to that next byte after the replaced instruction. And that means that after the breakpoint is done and we want to continue the program, we can't just return and go back to where that program counter was. We have to go to the byte before that, where the original instruction was. You know, not the address that was pushed onto the stack. So before we do anything, we need to back that program counter up to the original address. And also keep in mind that everything we do in this breakpoint hit handler, it's critical that we restore absolutely everything to the way it was before the breakpoint hit, so that when all is said and done with our breakpoint hit handler, all registers and flags, the stack, the program counter, everything has to be restored to the original values as if this breakpoint never happened. So, you know, less of course any changes that we allow the user to make to those values intentionally. And again, we're not going to do any of that modifying of registers in this one. We'll save that for later if there's enough interest in fleshing out this basic skeleton breakpoint manager. So the first thing we have to do when we get to this breakpoint hit handler is decrement the address that's on the top of the stack. So we use this XTHL, and the XTHL is possibly one of the most underappreciated commands. XTHL exchanges the top of the stack, where the T stands for the top of the stack, with the HL register contents. So we're not going to destroy anything, we're just going to swap the top of the stack, so that's our old program counter with the HL. So HL is going to go onto the stack, our program counter is going to come down to the HL, where we can now decrement it, and then we exchange again to put them back where they were. So now the original HL is back in HL, and the program counter is now back on the stack, but it's just decremented by 1. Now a key point is that neither the XTHL or the DCX changes any of the flags. So we, right now, other than decrementing that program counter that was on the stack, we haven't changed anything. But we wanted to do that first before we started pushing a bunch of other crap up onto the stack. Now that we've done that, let's save all of the registers, and we're going to do this in a particular order so that the flags will be buried. And when we start restoring things, the flags will be the last thing to come off. And we're also going to push the program status word, and then we're going to immediately pop that into the BC pair so that C will give us access to all of the flags. And a more advanced handler where we want to allow the user to modify the flags, we obviously need to pop the modified flags into the PSW. So now the program has saved everything, all the registers have been saved, and we can do whatever we want and later add whatever bells and whistles we want. We don't have to worry about preserving anything because we've captured all of those things. We can restore them when we're done. In the skeleton version, we're just going to display the register values. We're not going to allow the user to change them. But before we do that, so that the program can eventually continue, we first need to take back out our restart to instruction that caused the breakpoint and put the original opcode back in. So here we load up our little breakpoint table to get the original opcode address, and then we put the original opcode back into that address. All right, so now all the heavy lifting is done. After we do whatever it is that we want to do and however many bells and whistles we want to build in, all we have to do is restore everything and then just issue a return instruction. The program counter will get popped back off the stack. Since we decremented at 1, it will be pointing to the original instruction. The original instruction has been restored into that address, and so the program will just continue as if nothing happened at all. So you can see the power of this. We've just stopped the program, went someplace else. We can now look at all of the registers. We could add features to change all the registers. And then when we're done looking at everything, we can just tell the program to continue exactly where it was, with all the registers being the same. And from the program standpoint, other than some time passing, nothing has changed. Now the remainder of this breakpoint hit manager is just to display register values and then restore the original values and return to the regularly scheduled program. We're going to do the same thing for each register. For each register, we first send out a display message followed by the register value. First the program counter, and conveniently that's the value that's in our breakpoint table. So we're going to go back to our breakpoint table and get the program counter. Next thing we're going to display is the stack pointer. Before we send this out to the user, we need to correct it for the things that this breakpoint hit manager has pushed onto the stack. There's the original return address that the restart itself pushed onto the stack. And then we pushed 4 more things. We pushed program status word, H, D, and B. So that's 5 things total, or 10 bytes that we have pushed onto the stack. The DAD instruction, the double register add, is about the only way to get the current stack pointer out of the 885 register. But since we have this little offset problem, we load the 10 byte offset into the HL pair, and then when we do the DAD, we get those 10 bytes added to the value of the stack pointer. So we took the current stack, we added 10 bytes to it, and now we display the HL pair using this little send HL, which sends out the 4-character ASCII string representing the HL contents. And yes, we're adding the 10 bytes to the stack pointer since the stack is growing down. So by adding, we're backing the stack up to the higher memory location where it was before we got involved. You know, we have 10 extra things on the stack, but we don't subtract 10 from the stack. We add 10 to the stack because the stack is growing down. All right, the program then sends out the accumulator, the flags, the B, C, D, E, and the HL messages and the values just like we did before. Right now, the flags are just displayed as a hex byte, And we could get fancier later and call them out individually to save the user from having to look them up, since the flags, where they actually are, is buried well into the documentation from Intel. If you want, you can use my handy 8085 reference sheet. There's 5 flag registers in the flag byte, and 3 of them are just fillers. The least significant bit, bit 0, is the carry, bit 2 is the parity, bit 4 the alternate carry, bit 6 is 0, and bit 7 is the sign. And I'll put a link to this reference card down in the description. You can print it out. It's got all of the 8085 and 8080 codes on the front, and it has a handy little ASCII table on the back. All right, so where were we? We needed to save the HL for nearly last, since we needed it for all of these output messages. Once that last message was done, the message that indicates this is the HL register, now we can pop the HL pair and send the HL values to the terminal. Conveniently, these last 2 calls don't destroy anything. Then finally, we pop the program status word and do a return, and the breakpoint event is officially done. All done. That's it. We have written a complete breakpoint manager and the breakpoint handler in 15 minutes. So all done. Let's go ahead and test this. I have a little piece of code here that's already in the EEPROM. We just need to copy it over to the RAM. So let's use the copy command. In the EEPROM, it's at 7000, and let's go up to 7010, and we want to put that in the RAM that is at C000. If we look at the test code over here, we can see that all it does is it fills the registers with known values so that we can test if they were being restored properly after our breakpoint. So it fills the accumulator with a known value. It then does a compare with that same value to set one of the flags, to set the 0 flag, and then it just loads the BC, DE, HL, sets the carry, and then a couple of no-ops. So we'll be able to put a breakpoint in at various points in this to make sure that it's all working okay. So we've copied it over. So now let's look at it to make sure that it made it there okay. So let's do a dump at C000 to C010. So there's our code, 3E02 all the way up to the 3700, and then the C7 here on the next line. Now let's use the breakpoint command to set the breakpoint address. So let's do a breakpoint. If we go up and look at our actual code for our breakpoint, let's go back to our breakpoint code. So here's our breakpoint code. The first thing it's going to do is give us the message, and that's what we're seeing now, into the breakpoint hex address. It's now at the call get hex word. It's waiting for a hex word. When it gets back, it's going to test that. So let's do a breakpoint at, let's say right before it loads the HL pair. So let's do the breakpoint at C00A. So it's tested it and it's returned, somewhat unceremoniously. We could put in something here to say it was done later. Now let's go back and look at our breakpoint table. So these are the 3 bytes that we put in where we're going to store that address and the original opcode. So that is at, let's do a dump of E06A to E0FF. I didn't want to do the whole thing, but that's okay. So here's our E06A. We only look interested in these first 3 bytes. There's the C00A, that's Little Indian. That's where we put in our breakpoint. So that's our address of our breakpoint. And 21 is the opcode that we originally had there. So 21 was the LXIH. All right, we can look up here at our line of code. There's the 674521AB. So that 21 is what got replaced. Now let's look at our program again. So let's do a dump at C000 to C010, where it went 674521. Now it goes 6745D7. And we can see that the original opcode, that 21, has been replaced with the restart 2 opcode. Finally, let's run our program. So let's do a go to C000. Do we want to change program counter to that? Yep. All right, so it has run the program. It got to the target address where it hit that restart 2. The restart then sent it to the breakpoint manager, which printed out the register values. Let's look at the register values. The program counter is C00A. That's where we put our breakpoint in. That's correct. The stack pointer is at E0FD. So that's correct. The accumulator is the 2 that we loaded it. The program status word, that's actually just the flags, 5, 4. And then let's look at the BC. That's 0, 1, 2, 3. It did the DE, 4, 5, 6, 7. And then before it filled the HL, that's when we had our breakpoint in. So the HL is whatever value it was before our program filled it. Okay, so that's correct. It stopped it right between the DE and the HL fill. Then after the breakpoint, it restored the original opcode, it restored all the registers, and then it continued the program at that opcode. Now we can convince ourselves that that's correct. Let's do another breakpoint at a little further up. Let's put this breakpoint in at C00F. That's one of the no-ops. And now let's go to C000. Yes. And now we can see that when it shows the registers, it went all the way up. DE is 4567, HL is 89AB like it should be. So there you have it. That's a nice skeleton breakpoint manager that you can flesh out with additional features to your little heart's desire. Let me know if you'd like to take this further. But all totaled, there's one line of code at the restart vector table. The breakpoint manager itself took 9 lines of code, and of course, it utilized some pretty useful subroutines like the get hex word and the send string and so forth. But basically, there's only 9 lines of code for that. The breakpoint hit manager took 9 lines of code to save everything, and then about 30 lines of code to display the register values. And finally, there were 4 pops built into that and a return. So in my opinion, the ability to breakpoint is an incredible tool to have, for a 15-minute investment in writing the 50 or so lines of code that it took. And as useful as the skeleton version is, it could really use from a few pretty modest improvements. The first thing is that you notice that it removed the original breakpoint so that the program could continue, but since we can only have one breakpoint and it just took that breakpoint out after it was used, it really limits how we can use this tool since it's kind of a one and done breakpoint. So before adding any other bells and whistles, if we were to add anything, the first enhancement should be to allow the user to set another breakpoint before the program continues. And from there, I think the next thing it needs the ability to modify the registers before continuing the program. Those are kind of the abilities that any honorable breakpoint manager offers. And beyond that, it's entirely personal preference and one-upmanship kind of thing. Alrighty then, let me know what you think and what are your favorite breakpoint features. As always, this channel is entirely fueled by sharing subscribers' interest and engaging comments. Thanks for watching. I will talk with you later. Bye-bye.